In this video we're going to recap isomerism from earlier in the course, looking at the difference between structural isomerism and stereoisomerism, and introduce a new type of isomerism called optical isomerism. So we're going to recap on our previous types of isomerism and add that extra one, optical isomerism. So we're just going to look down the left hand side of this tree and look at structural isomers. Now remember from earlier in the course that structural isomers have the same molecular formula but a different structural formula. So the same number of carbons and hydrogens but arranged differently. They will have different names. There are three types of structural isomers. We've got chain isomers, position isomers and functional group isomers, three different types. We're going to have a look at the structural isomers of C4H8O. If you pause the video, you could have a go at drawing out some structures that you can make with 4 carbons, 8 hydrogens and an oxygen. Here are two of the structures that you might have come up with. These two structures have both got 4 carbons, 8 hydrogens and an oxygen, but are different in their structure. The one on the left has got 4 carbons in its longest carbon chain, so it's going to be called bute. The carbons are bonded with single bonds, so butan, and having a double bond O on the second carbon makes it a ketone, butanone. Whereas on the right we've still got 4 carbons in our longest carbon chain, so we're still bute, we've still got single bonds between the carbons, but now we're an aldehyde, so we're butanal. Butanal and butanone are classed as functional group isomers of one another because they have the same molecular formula, but their structures are different because they have different functional groups, functional group isomers of one another. You could have also drawn out a chain isomer of butanal. A chain isomer of butanal would have a different chain length, so instead of having 4, it's still an aldehyde, but now it has 3 in its chain, and the 4th carbon is positioned in as a substituent to that chain. And this is methyl propanal, and these two are classed as chain isomers of one another. So these methyl propanal and butanal are chain isomers, whereas butanal and butanone are functional group isomers. And you can see from my last two examples I've chosen to use skeletal formula just to mix things up a little bit. Also what you can see is I have drawn two structures that have an alkene, a double bond, and an alcohol group in them. So we've got bute 2-ene, 1-ol. That's numbering from this functional group carbon here. And bute 3-ene, 1-ol. I've moved the position of the alkene functional group, and therefore these two would be classed as position isomers because the position has moved. It's just a quick recap on structural isomerism and the types. So let's have a think about that other type of isomerism, stereoisomerism. Stereoisomerism is compounds that have the same structural formula now, but a different arrangement of atoms in space. So we're going to look at them having the same name generally, but having a different arrangement of their atoms in space. So there's two types of this isomerism. One that we've already come across, EZ isomerism, which we came across when we were studying alkenes, and the new one we're going to start looking at today, optical isomerism. So this is our new area today, optical isomerism. Let's just remind ourselves about EZ. EZ isomerism occurs as a result of restricted rotation about the planar, so the flat carbon-carbon double bond. Not all alkenes have this type of isomerism. So just test yourself out, see if you can draw, pause the video and see if you can draw but-1-ene and 2-methyl but-2-ene. So you can see I've drawn these out. On the left I've drawn but-1-ene and on the right 2-methyl but-2-ene. I like to draw, when thinking about EZ isomerism, the trigonal planar shape around the double bond so that I can see the structure and the arrangement in space. If you don't draw like this, you won't be able to see the arrangement in space, and therefore you won't really be able to see the EZ isomerism. Now, why don't these two have EZ isomerism? Well, it's all because one of these two carbons in the double bond does not have two different groups. So if we were to look at but-1-ene, we can see the left-hand side carbon has got two hydrogens attached. These two are the same, and therefore, whether you could rotate or not, you will not get a different structure. And in our structure of 2-methyl but-2-ene, we've got a methyl group. These two are the same, and so they will not make different structures even if there was rotation. For an alkene to exhibit EZ isomerism, each carbon atom of the double bond must be bonded to two different groups. So these two do not have EZ. Not two different groups on each C. We're just going to recap again on our Kahn-Ingold prelog or SIP rules for assigning E and Z. Once we know that something has an EZ isomerism, how do we decide whether it is the E or the Z? So rule number 1 is identify the highest priority group on each carbon, and remember that the highest priority group is the group where the atom with the highest atomic number is. So the highest priority group is the atom with the highest atomic number. Now, if you have two atoms with the same atomic number, then you're going to keep moving down the chain until you find the first point of difference. So we're going to keep moving down the chain until we find the first point of difference. If those two groups then that are the highest priority are on the same side, it is the Z isomer. And if they're on opposite sides, it is the E isomer. So let's have a look at our structure at the top. It tells us it's the Z, but let's see if we can understand why. So let's consider the left-hand side carbon. And we're looking at the first atom we hit, we've got a C or a H. C has higher atomic number than H. So we can circle round our highest priority group being the methyl group. The methyl group is our highest priority group on that side. If we look at the right hand side, we've got to consider the difference between F and C. Now F has a higher atomic number than a C. So we can circle around the F and say that that is our highest priority group. Now, because our highest priority groups are on the same side of the double bond, that is why we've come up with the Z for our isomer, Z isomer. It's quite easy to fall into the trap of looking at the size of the substituent and deciding that this ethyl group looks bigger, so it will have higher atomic number. It's not the size of the group, it's the first atom you hit and its atomic number. F is atomic number 9, carbon is atomic number 6, F has higher atomic number. So have a go, pause the video and have a go and decide whether each of these is the E or the Z. So if we have a look at these first two, we have in example number 1, the two groups on the left-hand carbon of the double bond are both methyl groups, so because they're the same, there is no EZ isomerism. And then on the second example, on the left-hand side, we've got a chlorine versus a carbon. Chlorine is atomic number 17, so chlorine is highest priority. And on the right, we've got a carbon versus a hydrogen, so the carbon of the ethyl group is the highest priority. Therefore, this is the E isomer. If you turn over, there are a few more for you to have a go at. So see if you can decide if they have EZ, and if they do, which one they are. So if you have a look at these examples, the first one, the Br is the highest priority. Br has higher atomic number than H, and Cl has higher atomic number than H, so this is the Z. The second example doesn't have EZ because the right-hand carbon has two atoms the same attached, so there is no EZ. And the next example, again, there's two ethyl groups on the right-hand side, so it's not having EZ. And when we look at the last example, the right-hand side is relatively easy. The chlorine is higher atomic number than the C, but on the right-hand side, they're both Cs, so we have to find the first point of difference, which makes the top group have a higher priority, and therefore the two groups are opposite. This is the E isomer. That concludes our recap of isomerism. If you move on to the next video, you'll be able to start looking at this new type, optical isomerism.